All right, welcome to video 2 for section 1.7. Sorry about that. Okay, so natural questions we can ask ourselves. What does it look like for a set of one vector, a single vector, to be linearly independent? Okay, so then we know what? This means that our single constant, this equation, has only the trivial solution. It's only true when c is equal to 0. Okay, so that means that so there's no solution. So no solution if c is non-zero. So if c is non-zero, then our equation is equivalent to v being equal to exactly the zero vector. So in other words, if there's no solution, means that this is non-zero, so it just means that v is not the zero vector. And so a single vector is linearly independent as long as it's not the zero vector. Okay, so the only vector by itself that's linearly dependent is the zero vector, is the other way of phrasing that. Okay, so one vector is maybe not so interesting. Let's do the next hardest version of this. Is what does it look like if we've got a pair of vectors u and v to be linearly independent? So let's assume, we'll assume the set u and v is linearly independent. So that means that so we can't, so that means that what? That for any C1, C2 in the real numbers, what should we have? Not both 0. No, sorry, we're going to assume these are linearly dependent for a second, and then we'll make a conclusion about independence in a second. So then, if we're assuming they're linearly dependent, means that we can find. So there are real numbers, not both 0, so that C1u plus C2v is equal to 0, the 0 vector. Okay, so since they're not both 0, we can look at two cases where C1 is non-zero or C2 is non-zero. So if C1 is non-zero, then what we can do is divide by it. And we can get what? C1u is equal to minus C2v. And if C1 is non-zero, we can say, well, actually, u is just minus C2 over C1v. V looks a little u-ish. Okay, so in this case, u is a multiple of v. U is a multiple of v. And similarly, if C2 is non-zero, we can play the exact same game. We'll have that C2v is equal to negative C1 u, and then dividing by C2, we can get v is just minus C1 over C2 u. And again, v is a multiple of u. And so if we want to capture both of these situations at the same time, we can say, well, the only time when two vectors are linearly dependent is if one is a multiple of the other. So their upshot, u and v are linearly dependent if and only if one is a multiple of the other. Okay. Let's give ourselves a little more room here. So a quick note and an example I want to give. And so the note is, this doesn't need to be true for more than two. So certainly we can have three vectors that are linearly dependent where no one is a multiple of the other. So this is particular to there being exactly two. So that's the little note is, yeah, this does not true in general. This up there is not true in general. It's specific to only two vectors. And the example we can take is, yeah, let's give an example of linearly dependent vectors where no one is a multiple of the other. So if we take, v1 to be 1, 0, 1, we can take v2 to be 0, 1, 1. We can take v3. Let's do the simplest possible thing and take the sum of these two. So that's just 1, 1, 2. Then clearly, no one vector is a multiple of the other, because any multiple of v1 would still have a 0 in the second spot. Any multiple of v2 would still have a 0 in the first spot. And any multiple of v3 would either just be the 0 vector or have no zeros whatsoever. So there's no vector here. So none of these are multiples of each other. None of these are multiples of each other. Oops. However, we can see really quickly, if we take v1 and add v2 and subtract v3, we do in fact get the 0 vector. And so they are linearly dependent. Okay, so this characterization of linear dependence really did depend on there being two and not just any number of them. Okay. We do have a theorem for two or more. It's not quite as nice as our theorem for just two, but that's the way it goes. Okay, so if we have a set of vectors S, that's a v1, v2 up to vp, two or more vectors is linearly independent if only if, at least one vector is a linear combination of the others. At least one vector in S is a linear combination of the others. Okay. And the book goes on to say something a little more specific. I don't think we ever need the more specific thing, so I'm gonna skip it here. If you're curious, by all means, take a look. I will point out that we have no control which one vector is a linear combination of the other. So note, there's no promise, no control, no promise about which ones are a linear combination of the others. Just that at least one has to be. Just that they exist somewhere. Somewhere in our list. V1, V2, up to VP. So can't say which ones they are, but they have to exist. Okay, so in particular, if we go back to our example up here, we should be able to say one of these vectors is a linear combination of the other two. In this case, actually, okay, so in this case, it is true. We can write V1 as a linear combination of V2 and V3. We can write V2 as a linear combination of V1 and V3, and we can write V3 as a linear combination of V1 and V2. Okay, so this is a special case. So in our previous example, v3 is equal to v1 plus v2. Okay. So that's all we can say in general. I've got a couple more theorems. These are mostly little shortcuts to deduce or exclude linear independence. So if we have, again, vectors v1, v2 up to vp in Rn, and n is less than p. So it means if we have more vectors than there are like dimensions in space, then it must be, we automatically have linear dependence. So yeah, more vectors than entries in each vector. So there's one way to think about this. So yeah, n less than p means more vectors than entries in each vector. So let's take a look at an example. We'll do the quickest example we can think of. We've got vectors in R2, 1, 2, 0, 1, negative 1, 1. We know automatically we've got three vectors and they're living inside of R2. So that there must be, according to this theorem, there must be linear dependence. It must be linearly dependent. Oops. Dependent. There we go. Right here we've got n is 2 and our p is 3. And sure enough, n is less than p. Okay, and there's one last little theorem. If we have a set of vectors v1, v2, up 3p, up through vp again, and it includes the zero vector, no matter what else is on that list, the moment we include the zero vector, we've got a linearly dependent set of vectors. And the idea here is that all we need is, yeah, we can do a quick proof if you like. Yeah, if you want to know where the proof is for 8, for 7, again, I encourage you to take a look at the textbook. I'm not going to include absolutely everything in these videos for sake of time, but for here, yeah. So may assume, yeah, let's assume, oops. So if we're including 0 in the set, let's assume that our first vector is the 0 vector. And then if we want to show linear dependence, all we need to find is some collection of real numbers, not all zero, so that the linear combination of these vectors with those weights, those real numbers, is the 0 vector. So we'll take 1 times v1, and now we can kill everything else off. We can do 0 times v2 plus 0 times v3 plus all the way up to 0 times vp. And that is equal to 0 because we've killed off all the other vectors here. Doesn't matter what they were. And we know v1 was equal to 0. So 1 times v1 is still equal to 0. So we've picked off some non-zero real numbers and ended up with a 0 vector. Okay, so that's a nice quick little proof. Yeah, I'll see y'all again for 1.8. Take care, everybody.